Hi. I had a couple people ask me if I could make a video for the Wiens Law activity for this, and I'll make a quick little video, try to explain the reasoning behind it. I'm gonna share my screen here if I can get to the whiteboard. Okay. So I'm going to give you some just slightly different numbers than your assignment has. And real quickly, I did have a typo. The constant, if you're going to use micron, should be 2900. I'm really not sure why I had 0.29. I guess it must have corrected to 29 hundredths. Anyway, let's say we had in a alternate universe, we had a sun with a peak wavelength instead of 500. Let's say it was 600 nanometers. All right, the first step is to find the temperature. So if you look at page 34 of your book, it talks about Wiens' law. We have a way of knowing the temperatures of all stars by looking at their peak wavelength, and that's explained on page 36 and 37. Anyway, Wiens' law gives you a relationship between peak wavelength and temperature. So I'm going to use nanometers. And so the constant, if you use nanometers, is 2.9 times 10 to the 6th. And that would be nanometers times kelvins over temperature. So if I know my peak wavelength, I can cross multiply and divide. And essentially, I end up getting my temperature to be 2.9 times 10 to the 6th nanometers kelvins over 600 nanometers. My nanometers will cross out. And I get a temperature of about 4,833.33 kelvins. I am the type of person that leaves everything in my calculator. If you are not, it is okay just to round it down to 4,833 kelvins. Our sun's surface temperature is about 5,800 kelvins, so this star would be a little cooler surface temperature than our sun. All right. The next step is to find the intensity, which uses Stefan Boltzmann's law. And this sigma is a constant, and intensity then is directly related to the temperature of the surface to the 4th power. If you've heard of intensity before, it's probably been in relation to sound waves, how close you are, how intense the sound is, and how much that can damage your ears. Light works in a very similar manner in this case. So to find the intensity, the sigma is a constant. It is 5.67 times 10 to the negative 8. And that is a watt per meter squared Kelvin to the 4th power. That is a constant. And then you would put your 4833.33 to the 4th power there. I am mostly concerned with your process on this. If you struggle with working the calculator for scientific notation, that's okay, I understand. But go ahead and give it a try. And so for this particular sun in an alternate universe, we would get an intensity of 3094353.75 watts per meter squared. Now, what this is telling you is that's how much energy per second the sun kicks out for every meter squared of surface area that it has. So if we took, I have to write this down, if we wanted to know the total what's called luminosity or power, or the total watts that the sun kicks out, you would just take that intensity, and I'm going to go ahead and change that to scientific notation, 3.1 times 10 to the 7th watts per meter squared. And let's say this star has a surface area of, so I'm gonna have to take that times a surface area. It's going to be a little smaller than our sun, so 2.5 times 10 to the 18th meters squared. If we multiply those two numbers, we get a 7.74 times 10 to the 25th watts. And a watt is a joule per second, so it tells you how much energy per second the sun is kicking out. So if we want to know how much energy it kicks out in the course of the day, and that would be our total energy, we would just take the 7.74 times 10 to the 25 watts times 8,6400 seconds in a day. And that would tell you how much energy it is kicking out, which comes out to about 6.68 times 10 to the 30th. Okay. If you look on page, I wrote down the page. If you look on page 41, it talks about the solar constant, and that's how much of the sun's energy hits the Earth at a 90-degree angle. So the sun kicks out, let me go back, whoops, let me go back. If the sun kicks out 7.74 times 10 to the 24th watts, or this fictitious star, not all of that hits the Earth. Obviously, that's over the whole surface area of the sun, but the part that does hit the Earth is offset by the inverse square law, because the Earth is about 93 million miles away from the sun. And so the actual amount of energy that hits the Earth from the sun is what's called the solar constant. So when you get done with your calculations, what you should get for the luminosity is somewhere around 3.94 times 10 to the 26 watts. And then you would take that times the 86400 seconds to get the total energy in the course of a day. When you consider how far away we are, about what gets to the Earth from the sun, the amount of energy per square that hits every square meter of the Earth, that is just under 1,400 watts per meter squared. I hope this helped a little bit. Feel free to reach out to me if you have any questions.